One, two, three. Ah, here it is. It's back. Okie dokie. Thank you, James. Test, sound test. Good. Looks like it's working. Convert it to this. Go. Hi. Morning. Morning. I work here. Good. Hi. Hello. Everybody take cookies, coffee, and tea. Free. Okay. By the way, just quick question: who is really like beginner? Like, raise your hand. Like, okay, so you do not know concepts of deep learning, sort of, ish. Okay. So I know that we have some advanced people over here. So a different game. Okay, everybody settle down. Are you sure you don't want coffee or cookies or anything else? Perfect. Okay, so I was asking who's really a beginner because this is an introduction to PyTorch and we're going over the core basics. Okay, so welcome to this series of data science it's a series for data science, but now it's very wide and very useful. So let me introduce myself. I am the handsome guy in this picture. I'm Didier Barradas Bautista. This is the KBL team. We are always doing this series of introduction to for data science. Last week it was Shell and Git. We have also introduction to deep learning. This is kind of an introduction to deep learning disguised as PyTorch, but it goes alongside. The other courses focus on TensorFlow. And so we have other kind of introduction. I am in charge, for example, of the introduction to people to IBEX. So, well, you probably have seen my face around. So here in the KAUST core lab, the visualization core lab, we have several projects. We're actually actively searching for helping you guys. If you have a project that we can help, please come and talk to us. For example, we have there projects that make about visualization of events, weather events, made by James. Segmentation and visualization in VR, AR is done by Ronald. We have here my specialty in biology and data science all over the place with these other projects alongside with my colleague Abdul Rafur Halimi. We are the two data scientists in the team, and obviously we specialize in Crunchy's number. Okay, so along that, we have a YouTube page where you will find several videos, just like this one. You will find the recording of this session there, alongside another ones. Like, for example, here you can see the talk of my colleague Abdul Rafur. It also have an Arabic version that you can see over there in the corner. All the data science sessions that we have done every year is a little bit different topics. Some of them are also like data science onboarding, but on our HPC facility, our HPC computer called IBEX. Some other tutorials, like for example, setting up your Windows computer for data science, which is something quite popular. So we will, you can subscribe and like our videos so people get noticed. All right, so why PyTorch? Back in around 2014-ish, or I should say 15, there was something called Café 2, and that was part of the first frameworks that people use for deep learning. It was pretty popular. And then TensorFlow came around, and TensorFlow became really popular. And you can see here in this plot how it went from popular to be really small usage across time. So right now, PyTorch dominates the scene. And why is that? PyTorch is more flexible, is compared to TensorFlow, more Pythonic in the sense that it allows you to play around with the bits and different parts more than with TensorFlow. Also, it helps that several communities, like for example, if you know PyTorch, it was developed by Facebook, now Meta, meaning that companies use it. So it's a company level thing. Also, Elon Musk, Tesla, and all these guys are using PyTorch. Your favorite LLMs, ChatGPT, was probably built on this. So many other things that you have already used are built on PyTorch. So this is outdated for 1 year or ish, but the trend is the same. You will start seeing code made in PyTorch several times. It doesn't mean that the others are completely dead, but they are not super used in the wider setup of enterprise and academic. Okay. So for this workshop, please go to this website. You probably already have over there this link. So in wiki.biz.kaust.edu, you will see a small part here in the right side that says training events. search for the one that says data science. This is not the spring series 2025, but you will find this one now. This, please click here in Introduction to PyTorch, because it will deploy all the links that we are going to use for this workshop. Okay. So give you a minute to go over there. Well, when you click in Introduction to PyTorch to Data Scientist, before I said something, in this page, you will also find on the bottom all our past workshops from the different persons in the team. There are workshops from Aviso, which is for segmentation, from my other colleagues. There are other workshops, like, for example, the Arabic one and the deep learning. This workshop will be there in time. So we have also in the bottom the archive of all the workshops that we run. Okay. When you click on that, you will land in some page that looks like this, right? So there, at your right, you will have these materials over here. I will put the slides that you're seeing here over that page. And originally, we were going to use something that is called ClassHub. But ClassHub is down. I put something there that says Binder Hub. So it says public binder. Click there, because it will take you to a GitHub page. So if you don't find the link to that GitHub page, it's this GitHub page. Okay? So in this GitHub page, you scroll down to the README part, you will find these two labels called launch binder. So originally we had a binder for KAUST, meaning like this is a virtual machine that you can access, but right now it's down. I talked to the guys that are managing this. So in this very moment, you can click in launch binder, the normal one. This is a very small resource. We don't need like a very big computer for running this workshop, but you can click here. Now, because I know that it's a small, very small resource, we also have this option. If you want, I convert all the notebooks of this workshop into a Google Colab version. Now, you can use this one because it's basically the same. PyTorch is already installed in Google Colab alongside with NumPy. So why don't you try this one, for example? Just clicking one of the links, search for it. It's in the same web page. It's all the way down. It says like PyTorch workshop on Open Colab. Okay? And it will deploy something. Now, to tell the truth, this is cheating. Because if you have a Google account, it will allow you to use also Gemini. And given the nature of this one, this workshop is very basic. Gemini will give you the answers to the exercises. So, I don't know, whatever you like. This is good for me. So go ahead. You can click here or click on Binder, whatever you want. It's up to you. But please go to this web page. I mean, you have to land in this web page. GitHub, KAUST-bislab/introduction to data science workshop. There is all the material that you need for this workshop. So everything is online. You can access it whenever you want, wherever you are. Cool? Okay. Did you find this web page already? Everybody on track? Good? All right. So here I have a divergent question, and I would like you to answer. Do you like to see the skeleton of what you have to write or you will encounter in a code written by PyTorch? Or do you want to explore the concept of deep learning? Because there are two things. The concepts of deep learning are core concepts of deep learning that not all of you know. It might be candy later. Or we can check how you should read PyTorch code, so you can understand what is going on. It's a little bit tricky because both things are interconnected, but I will let you decide. We go to this part or we go to the core deep learning concepts. So who's for the PyTorch code structure? 1, 2, 3, 4, 5, 6, 7. Okay. And who's for the deep learning part? 2, 3. Okay. So you lose, but it will come after. All right. So for those of you that doesn't have like the core concepts of deep learning, don't worry. I will not get too deep into it because basic PyTorch code structure is going to be basic reading technique for you. So let's start. Now, what does a classic deep learning program needs? In the case of PyTorch, well, in general, like you need a deep learning framework, meaning is TensorFlow, is Caffe, if you still work with that. Nobody works with that anymore. And PyTorch. A framework is basically a battery of libraries that you can import and then you can work and use the pieces together to do one code. So in this case, it's PyTorch. It needs an optimizer. The optimizer, read it as a strategy that you're going to use to train the neural network. It's a strategy in general. The loss function, and this is one of the concepts that confuse many people, is a target that you want to minimize. Loss function means like it's a actual mathematical function that you want to go to zero, as close as zero as possible. And that's important. You need an activation function, and that's the confusion of many people. Like an activation function and a loss function are not the same thing. An activation function is a decision-making process. It's something that allows the information to pass or not. So these parts together, they are basically controlling the flux of information. Obviously, you need a neural network, meaning the architecture. For those of you that do not know, like you have different architectures, meaning like you have different kind of layers, you have different number of neurons, blah, blah, blah. That's an architecture. That's what I mean by network. And of course, you need a dataset training as tensors. And for those of you that don't know tensors, I will explain later. But the dataset has to be tensors, meaning that it's a matrix of matrices. Great. Now, the first thing you will find in any Python code is importing libraries. And in PyTorch is no different. Now, here I explain like what is doing each import. Like if you would just import Torch in Python, it will import everything inside of PyTorch. But the most important part is when you start importing things that are more finite. Like for example, Torch NN will allow you to build the architecture. So you put torch import.nn, and in your code you will use nn.something, and it will bring a piece of the puzzle together. This data loader here is a program specialized so you can push the information into the memory and then feed the neural network with it. The functional is what will give you the loss function, that thing that you want to get down to zero. Okay? And obviously, because this is so well built, it has also some things that allows you to manipulate the data on the fly. And because obviously I'm not the only doing workshops, it has a lot of data sets that you can use and we will use for this demo. So the first thing that you will find, also you have to find, is setting up the random seed. So if you don't know what's a random seed, it makes your aleatory component of the training predictable. So after you do this, you have to find this inside of the code. If you don't find this inside of the code, every time you run your code, it's a different result. So therefore, not reproducible. So please, when you write something, write this one just after it, set the random seed to a number. In this case, it's 42 because 42 is, in the Hitchhiker galaxy, the answer to life. geeky stuff, I know, but you can put 101, whatever number you choose, just set up the seed. Okay, the next part is actually the data sets. Usually you will find a section that is about the data, and in PyTorch it's really easy, and you will find that many people complain about data loaders because those are talking to the CPUs and they are importing the data into the memory. In this case, we are invoking something called MNIST. MNIST is a data set of different numbers written in grayscale. So here you can define like, hey, bring from the data sets you have, because we imported data sets before, from the MNIST, download it in this folder, train here, like train equals true, mean like you're going to label this part as train. It's going to download from PyTorch the things, a repository, and then it can do transformations. What does transformations mean? Data manipulation. If the image can be rotated, can be clipped, can be put upside down, that's the thing that transforms those. And we have many transformations inside of PyTorch. The same goes for test set. We set train and false, and that's pretty much the only difference between these two parts. But you need these two things to actually train a neural network. You need a train set, obviously, and then you need something that is not the train set that you need to test. So you can evaluate the performance. That's fine. You will find all data sets here in this specific direct URL. You can find that it's not only MNIST, you have many others. So when you give this workshop to the next generation, you will find there the list of things that you can personalize your workshop. Okay. Next. So I was telling you about how data loaders are usually an issue, and that's because you have to be able to decide when to use and how much data passes from your CPU, for example, to your GPU. This is more related to the GPU memory, because not all GPUs are created equal. So if you know, like a GPU, we here have many different versions on IBEX. We have old ones that have only 12 gigabytes of memory. We have new ones that have 80 gigabytes of memory. So that one makes a big difference, meaning like you cannot feed the same amount of information to the old ones than to the new ones. And that's the batch size. That's what it's expressing. A batch literally is just a subset of your training data that is going to the memory. The CPU is going to package, send it to the memory of the GPU. In the GPU is going to be fed to your neural network, and then the result is going to get back, and then you're going to give away another set of 64 different features and labels, meaning another time the CPU is going to get another package and send it and back, and that set back, and that creates a loop. So that can lead you to overflow the memory of a GPU if you don't set it right, or if you are not aware of it. Like the bigger the batch size, the better, because theoretically you will find that it creates bigger matrices that is better for the formation of something that we would call gradient. You will see in one of the notebooks something called AutoGrad, and we will go to there after this. Okay, so after you do this, you can select, let's go back. Okay, so after you do this, you select the data loader that is going to basically connect the memory. You want to input the data, and you want to input how much of that data is going to the memory. The same for the test, and you can write this a small snippet of code just to check that everything matches. That's perfectly normal, and it's something that I advise you to do. It's a small unit test just to check that everything is on your correct side. Okay, now comes the really difficult part, which is the body. Now, this slide has so many things. Like, for example, who of you knows what's a convolution? Like 1, 2, 3. Okay, 3 persons only know what's a convolution. Nice. So a convolution, technically speaking, is taking a matrix that you see here, and you're going to reduce or compress the information of that matrix into a smaller matrix. So you have there different things, like you're going to use something called a kernel, which is represented by these 4 squares here. And then the projection from this matrix to this matrix with a stride of 1, meaning that it's going to move just one cube at a time, is what actually allow you to sample all the matrix elements and try to compress them to smaller matrix. That's a convolution. So in this very complicated skeleton that I put here, what I want you to understand is also this diagram. This diagram here talks about how people represent a neural network. It starts with an input, and then the input gets transformed by these cubes. This is what it represents, each transformation. And then between them is the so-called layers. It has neurons and so on and so forth. And in this class, ComNet, you will find it in all the PyTorch code. There are 2 parts. First is the bones. In this part, you will always find def, that's just init, self. And here is a list of what you want to use. And then the def forward, which is the second part here, is the flux of information. So there is how you want the information to be treated. Meaning you import first what you are going to use, the elements, and then is the flux of information. In this case, the def forward starts like, okay, here's the convolution, this is in green. Then I apply a mathematical function, which is my loss function, then another convolution, blah, 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 blah. This is why I put here these arrows in green and these parts here in red. Okay? So basically, when you find this kind of representation, don't fear, it's just an abstraction of this code. Or it can be seen the other way around. The way to write this in Python is this. You first import the elements, and then you establish how you're going to use those elements. Okay? I will come back to this one with another kind of, if you want, we can explain what's going on with these numbers here, but that's for later. All right? All right. After you have all that, and that's the big chunk of code that you will find, then you start defining your strategy. Like I told you, there's an optimizer. You have already a loss function that you can call with NN. We already see that you import torch NN. So this is how you call it in PyTorch. NN dot something will import one of the loss functions. The optimizer, which is the strategy, usually you will find that for some problems it doesn't work, but you will find SGD, which is stochastic gradient descent. That's the strategy that is going to update the information in the neural network. And that's pretty much in the loop all the time. So when you invoke this optimizer, you basically are telling him like, hey, I have a model, optimize these parameters, meaning update them. And you have the famous learning right here, meaning that everything is coming together. This is just the last, almost the last part of the code. You can do this. Usually it's a good practice to have device really on the top, because you can have a Mac, you can have only CPUs, or you can have an NVIDIA GPU. And actually you can have now even the Tensor from Google. So Torch supports many of these, like MPS is for Apple, for example, GPU if available. You can change this manually, or you can do a clever bit of code that will change it for you automatically. But that's pretty much it. And why do you want this? Because you want your model to live in the memory of such device. So this part here will send your skeleton to the memory of the GPU. And then it will send also the training batches over the memory. That's why it's basically saying here, like, send it to the device. So in some cases, this is a thing about going faster or going slower, depending. So I put here a list of precisely all the optimizers that you can find, because SGD is just one example. but you also have several loss functions. In this case, cross entropy loss is one of a kind. It's not the only one. Okay? Now, for this one, it works because what I'm showing you here is something called AlexNet. This is one of the seminal AI models. They are also like one of the simplest, quote unquote. Okay. So before you train, you actually, what I advise is you find this definition of the train. So in Python, you know that you can isolate things in a definition, meaning that this bit of code, and actually this, I hope I didn't create a monster here, but the right side and the left side are exactly the same. They have only a few things different, but the idea is the same. You're going to use a model, you're going to use your data loaders, and you're going to use your optimizer and your loss function. So in this side, in the left one, we are defining the size of a len because this variable here is going to be used all the way down here just to let you know how much it has progressed. It's not consequential to the actual training, but it's for you to know where you're standing. It's the same here. All the way here is the same idea as this part here. Okay? So this one is not super important for the training. It's just for you to know where is it going. Now, what is important is like model.train. That will trigger then the training mode for the code. And here is the loop that it will go over the data, and it will say like, okay, give me the first batch, the first group of these two things, the images and the labels or whatever I want, and whatever I have, the features, and what I want to predict. The first group, send it. We're going to put it on the device because it's going to be living in the same memory space as my model. And then we're going to predict. We're going to see how far am I from the zero. And then I'm going to send back that information and update the neural network. And again, until you run out of batches. The same happens here. Pretty much straightforward. You have a batch index for each of these small groups. Give me my features, give me the label I want to predict, and then send them to the memory where my model lives. Let's calculate then how far am I from the zero, and then update that part, update the neural network, and do this until you reach zero. Technically speaking, you want this to go all the way down to zero. If you go all the way down to zero, great, you solve the problem basically to the perfection, or you overtrain your neural network. But okay, and this part here that you see on the bottom is just how to print it in the terminal, how to print it in the output. It will tell you like, I'm in the 1% of the data, I'm in the 10% of the data, I'm in the 20, until you see like, oh, okay, it finished. Okay, with all the batches, and it's gone through all the data. Perfect. So you also need to do this for the test set. You have to define that you're going to use the model, but the only thing that you're not going to do here is to update the model. This is why in this line it says with torch no grad. It means like I'm just going to test whatever is trained on. Whatever my model learned, now I'm going to test it and nothing is going to be updated. I just want the result. And this is pretty much what it says here. You're going to use, again, the data loader, but this data loader is the test set. And it's going to give, again, the batches, send them to the memory, evaluate the test loss, meaning how really far am I from zero, and then get pretty much an accuracy level. There are some other measures that, depending on your problem, will be important, but accuracy is one of that everybody understands, right? Okay, fine. This one is the training phase. Now, here, as you can see, we have something called epoch. Epoch is how many times you're going to pass through all your data, not the batches. So in the training, we pass just bits of data. But then you probably want to do this again and again, so the neural network actually finds the information that is valuable inside of that training set. So an epoch is defined as a complete pass of all your training data. You want to do this as many times as possible, trying to get those losses, the loss function, as close to 0 as possible. And this is why here we have the train definition, getting the train data loader, the model, the loss, and the optimizer. So what I want to go to 0, the strategy to update is, and then I'm going to test it. For each time it passes the complete set of data. And then when I'm done, that's my final performance, that's my final model. Somebody can do this for thousands of epochs, somebody can do it for 50 epochs, and that's it. It depends on the number that you will see here out of the test and out of the training, precisely if you should go forward or stop way before. And of course, nothing of this matters if you don't save your model. So please save your model. As a matter of fact, it's a good thing that PyTorch call it checkpoints. What does it mean? That you can restart from that point forward. So if the lights goes out, your computer kind of dies, and you haven't had one checkpoint, you have to start over. But if you do a checkpoint every, I don't know, 100 epochs or something like that, you can restart from that point forward. And that will save you a lot of trouble and a lot of headache and a lot of time, because you don't have to restart from 0, from scratch. You just have to go forward. Okay. So apart from that, before we move to this, let's go over the notebooks, because I want you to see the notebooks right now. Let's go over here. Introduction to data science. Okay. So my original idea, it was for everybody to use the binder. So in binder, you cannot do cheating. But for each time you have one of these, you write the code in this section. And there is a solution attached to it. So if we run it, for example, in Google Colab, if you do not know the solution of each of these cells, you can deploy it here, and you can copy paste it, okay? So for example, let's go over practice NumPy. In this case, write the code here. Nice. So let's see, import NumPy as MP. This is a normal thing to do. Run anyway. And it will just import NumPy in this case. Now, here, if you know how to use NumPy arrays, you can do np.array. So it has already here built in a function that is similar to the Jupyter notebook, that it will autocomplete stuff. Actually, let's go. And if you don't want to cheat and really put your brain, data science, onboarding. So if you push here in binder, it will open in a bit. Okay. This is basically loading a virtual machine for you. Okay. Very simple virtual machine. Once it's launched, it will deploy something called Jupyter Lab, and it's the same thing. Now, in this case, you will have to go to the notebook folder. You can deploy practice NumPy. And you can do exactly the same thing. Import MP. Let's blow this up. Over here, here, numpy as MP. And then we can do dot tap. In Jupyter Lab and in many other UIs, meaning the development environments, if you put, for example, MP dot and then tap, it will open a menu where you can actually use all the functions there, and you can just circle through them. If you do a range, you have different other functions here, instances, as a matter of fact, and functions that you can use, like argmax, the biggest number inside of an array or a list. In arrange, example, 1049, and it gives me an array. Is this the solution that I was looking for? Well, yeah. Actually, I messed a little bit with this, and that's it. So what I want you to get at is, like, you can really test yourself looking at this, and if you are in some moment where you cannot actually answer what is in these cells, the answer is provided just below. Now, let's go to NumPy, and then create a matrix. Actually, this is more more difficult. But if you do the same thing over here, which is the beauty of the LLMs now, so here, the LLM is helping me to, well, not exactly cheat, but code quickly. This is Google's AI, and this is the right solution. I do not know if it's looking at the solution that I put there, but it's really just giving the solution because it has all this information inside. But I think it's actually pretty cool. And this is exactly what I want you to get. Like, the output is going to be this array, and it goes from 0 to 8 because it's 9 different numbers, but now it's arrayed in a 3 by 3 matrix. It's really simple. It's really straightforward. And I hope all the different notebooks are pretty much the same. Now, in this case, let's go to Introduction to Data Science, Tensor Basics. Let's open in Colab, why not? Okay, so let's start with this exercise, okay? Then after this one, we can do a pause, and then we can get into the core deep learning concepts. So first, what do we have to do here? Import NumPy and Torch. Like I told you, the one thing that is very important is that Colab now allows you to import Torch out of the box. Why is this? Currently, last year, PyTorch got updated to use Google's technology, meaning the tensor, the TPUs they have, the tensor processing units. If you do not know what that means, it's like we have CPUs, which is your standard and normal computer that you have. Different architectures of that has been spawned. Like Intel has one, Mac has one, but they are CPUs. Now, NVIDIA came and changed a little bit the game with their GPUs that were meant for gaming, and then somebody figured out that you could use that to do matrix multiplication. And matrix multiplications are way faster than sequential multiplications. So then it was like, hey, we can use this to really go fast. And that's why we have GPUs now as a backbone for AI and machine learning. But Google, seeing that they didn't want to get into NVIDIA's business, they designed their own chip, which is tensor processing units, TPUs. There are others around the world being developed, but NVIDIA doesn't have a complete hold on Google because they have their own machinery, let's say. If you go to Google Cloud, you will find NVIDIA GPUs because they bought it. They are not dumb. But they have their own stuff, which is important. Now, PyTorch can run equally fast in the TPUs and in the GPUs for most of the problems. Okay, but let's go and let's do the second one. So here is the predictability part. You want to do, there you go, random seed. So what we are doing here is exactly what I told you in the slide. This will allow you to control exactly the numbers that are going to happen every time that you run this. You will get the same result. Awesome. And then pretty much I put here that you can add this semicolon so you don't get this. Kind of the same, but you know, if you just want to get out of the way that small hex thingy here, you just add this small semicolon. That's it. Nothing to worry about really, but sometimes it bugs. It just looks like a very bad bug and people panic. Okay. Now let's create a NumPy array called MP array from this data. You can edit this here, by the way. Great. But then if you have data, you just have to copy this guy. Say, okay, that's my data here. And now with NumPy, you just declare array data. But we need this to be called MP dash was array. And does this match the solution? Absolutely. As a matter of fact, let's put here print MP array. And that's it. Okay, pretty much this is a well-known matrix. Now let's create a tensor. Torch actually, Torch, will allow you to quickly convert this array that we have here into a tensor. And like I put here, you see the normal NumPy array that expresses a matrix, it has these square brackets. And it's just a small matrix. Pretty much everybody can understand it. Here, it adds a property that it allows it to go into the memory of Torch as a tensor. This is important because now the library will understand, hey, we have not only a matrix, but this could be a matrix of matrices. This could be the index of another matrix that we have to look at, not just the number 1, or not the number 2, or 3, or 4. Great. We can create a lot of different things with Torch that will allow us to actually test. I put here a link, and if you click, it will redirect me. Go. Redirect. Come on. Internet these days in KAUST, right? Aha. Go to the documentation. Okay, let's see, PyTorch, Torch 1. Okay. Wow. Internet. Anyway. So if you have the bad luck like I had, that your internet is down like by a considerable amount of speed, go to the documentation when you have time. It's important that you know where the documentation is, because at the end of the day, it will show you all the tricks and all the available tools that you have. So in this case, I wanted to use torch once, torch dot once like x data. This is going to create the same matrix, the same tensor, but it's going to be only once. NumPy data. Let's go from here. Okay. Torch dot one like. Not x data, it's just data. He doesn't like it. That's curious. Okay. This is why I put here the solutions. Go back, go back. Go. X data is not defined. I know it's not defined. Of course. I forgot to rename these as data. Now we have the tensor. Aha. Rookie mistake as always. I didn't put this into, I didn't assign this tensor into a variable called x data. And here I was actually telling him like, do this from x data. The LLM actually did that. And I did not see this problem here. But okay, fix it that. I assigned this tensor here, that it should be 1, 2, 3, 4. As a matter of fact, let's add here print x data. Good. So here I have a tensor that says 1, 2, 3, 4, 5. And here I have only ones. You can do this the same, but generating random stuff. And then print. So there are different ways of how you can basically alter the content of a matrix or create similar matrices, but now as a tensor inside of the same PyTorch framework, meaning that you can basically alter these to make dummy sets or to literally create new matrices from where you want to start. But given that we set up already the random seed in the beginning, every time I run this, it's going to be the same result, once and again and again. Perfect. Now, let's go with this one. Let's start with, let me see if this works. HTML. Ah, it finally opened. So yeah, before I continue, this is the actual user documentation that this is going to be your actual guide of how to use PyTorch. In here, you can see all the definitions or all the components of that definition. Meaning for torch.once/like, you can pass even the device. If it requires to update a gradient, we don't need that. And even if you need to put this into a memory in a very specific way. But it also will give you an example at the bottom. So whenever you have a doubt, go to the documentation and keep going. Okay. In terms of basics, let's start 3 new tensors and then print them. So in this one, we're going to start tensor, torch. That's not manual seed. Okay, one with tensors generated by run n. Okay, here it is. Super quick. So you can start 3 tensors just like this. These will be random numbers, these will be ones, and these will be zeros. Let's put this as random. equals ones and zeros. So these guys now are there. Let me print this also. Random, ones, and tensor. Good. Like that. Well, as you can see, the basics are pretty basic and it's going pretty smooth. It's something that you can do because this is boilerplate most of the time. You can use shape also to modify it. There are another things like you can print the attributes of a tensor just like you can print attributes with NumPy. NumPy has the same kind of utilities. But for example, here, just create these ones again. Very quickly. The difference between these guys here is that they are linear. And these guys over here, when I pass shape, mean it's going to do now 2 columns, 3 rows, or 2 rows, 3 columns, sorry. 2 rows, 3 columns, 2 rows, 3 columns. And it just creates very quickly a matrix. Fine with that. Okay. Here is the part that is pretty much interesting for all Python intensive purposes. How do you select from a very big matrix or a very big array just a part of it? What if you're interested just in one row or just a bunch of rows, or even to skip some numbers? So in this very nice diagram, you can see that if we have something called a matrix A or array, you can declare like, okay, give me just 3 and 4, meaning like from the row 0, give me elements from 3 to 3 to the 5, but exclude 5. This is very Pythonic. So it will take these two. When you want a complete column, it's like, okay, don't do that. Don't do any row yet. Give me all of them. This is what this means, these two points, comma, give me the second column, meaning 0, 1, 2. Remember, Python always starts with 0. Indexing starts with 0. So this is a complete column, and you can see it here highlighted in red. This is more tricky. The green one is like, okay, give me every two elements starting from the second row, go to the second column, and then to the second element of that. This last part here is basically what it's telling, like skip X amount of different elements, meaning it starts here in the second one, goes and counts 1, 2. This is the skip part, and then gets that number 1, 2, skips the other part. Pretty intense if you want to do just this, but it's part of the manipulation of arrays and matrices. You can do this the same way with NumPy, and PyTorch will allow you to do the same because it's pretty close to it. This one is more like, okay, give me just the last part. If I know the shape of this matrix, I can just get one bunch of that matrix, and in this case, it's just telling like, go to the 4th row and give me everything from the 4th row down, and give me everything from the 4th column down, or from then on. And that's exactly what it does. It takes all the columns and then all the rows starting from the 4th. That's a normal way of doing indexing and slicing. And this is how it works for most of the programs like Pandas, NumPy, TensorFlow, and even PyTorch. Okay, so the last one. What did I want to do here? Slice from the following tensor and gets the first row and the first column and the last row. So if we declare this tensor, let's just put it here, tensor, that's nice. But then if I just want to print the first row, it will be that tensor. What I want is the first row, first column, and last row. The first row is just doing this. This is the part. The first column is like this. So as you can see here, the 2 points are there for filling the space of rows. The first element in this indexing is always rows. The 2 points will tell you, like, give me everything. So if we run this, I will have only this row and only this column. Let's print the tensor itself. Print tensor. Okay. So I will not see any difference, but at the end is the same. Like, this is the first row, this is the first column. And to get the last of the last element, print the last element will be tensor. And then -1, -1. And pretty much, if you do -1, -1, it will go to this corner here and get only that. If you do this, for example, now it will take the last column, or the last, this will be the last row. And if you do the same, but with the other part, print, not what I wanted. Okay, the last column could be like this, and also could be like this. Give me everything. Good. I like more this. So this is the last column. You can basically slice and pretty much get rows, single elements, columns, whatever you want. And this works also for NumPy. It works for TensorFlow. It works for PyTorch, because the logic inside is a Python one. Okay, let's do 5 minutes break. Like, you can get coffee, you can get cookies. And after that, we can go back a little bit to the core elements of deep learning. test. Okay. Okay. For those of you that are starting with deep learning, I compile a bunch of different information that comes from somebody that I think has a very good idea of how to communicate complicated concepts, which is Chris Albon. And he did this AI flashcard. So I didn't do the cartoon that you see here, but they are quite instructive. All right. In machine learning, what we want is basically a computer to do some kind of pattern recognition that is very complicated, but then it learns some features, it learns something, and through an iterative process, basically, we have something that can predict what we want. Perfect. Now, to do that, you need three sacred tests, three sacred sets. One of training, one of validation, and one of test. Why do you need that? Because while the machine or while the algorithm is going to learn, you have to deal with something called overfitting or underfitting. What does it mean? That your prediction is either too fine-tuned to divide your data points, or is too lax, and then it's allowing too much noise to enter to that prediction, meaning you have a higher number of false recovery rate. So what you see there on the left, on your right actually, is what can happen. You have a sample that has X's and circles, and then you train an algorithm to divide those two groups. You know that there are two groups, but you can do underfitting by doing just a regular linear regression. It will divide your data points, but then you will have a bunch of the data points misclassified or in the wrong group. While you can do the other opposite direction, which is like you are really good at dividing the two groups, and then when a new data point comes with a different shape, it just fails because it cannot improve or it cannot adjust what it has learned from your training data. So that's overfitting and underfitting. So for deep learning, the motivation was like you have high dimensional data. What does that mean? It means that you have something that is more than just tables. The keyword here is high dimension. For example, photos, we have pixels in 3 channels, and those are 3 dimensions. Okay? There are 3 matrices. And there is the relationship between them, and the relationship of the value of that matrix and the image you see. Okay, so deep learning is great for videos, images, and sounds, but it's not great for tabular data, meaning your Excel sheets. If you have something that is more like an Excel sheet, not going to be the best approach. And as a matter of fact, we call it deep because we can do a shallow network. Test. Something happened to the mic. Anyway, so what I was saying, like you have the deep part comes because you can do a shallow network, meaning like you have a bunch of neurons connected through it, and it's just one layer, which is what you see here. But it's called deep because it's better to have, for a computer, the layers spread around different levels, and then you have your inputs, which are the squares, and it goes through one level, the other, and they are highly connected. This is what deep comes. That's the deep part of deep learning. Well, what is a tensor? Like I was telling you, like we already have created tensors in PyTorch, and it's like, it's a matrix. So visually, I wanted to show like, you have a matrix here, but a tensor means it's a matrix of matrices, or a bunch of matrices, And that's exactly what this grumpy cat photograph is representing. You have these 3 channels, and each of these can be basically spread out in 3 different matrices with different values. That is what a tensor means. This is why it's also very good for deep learning to go over this data, and not so good for other classical machine learning approaches, because the relationship between these 3 channels gives you back this image that you're seeing. Now, that's high dimensional data, and everything can be expressed as a matrix. If you can express your problem as a matrix, you can probably use an approach of deep learning. I was telling you about the MNIST dataset that we saw in the slide. This is the MNIST dataset. And what people that start working with this problem did was basically express what they see here as a bunch of zeros and a bit of different values according to how black it is, right? This is the most easy way to approach how is something written in black and white. But it can be overly more complicated if you have the 3 channels or more channels, like, I don't know, instead of RGB, the whole spectrum of HSV, which is a gradient of different colors. So if you have a problem that can be expressed as matrix, like, for example, a network and an adjacency matrix, you can try to attack it with deep learning. Now, when we're talking about deep learning, I was talking about a lot of neurons. So a neuron, an artificial neuron, as is depicted in this diagram here, it's just a bunch of things that happens one after another. It has an input, it has an output. Between them, there is something called weights. Here, this is the core of the neuron where a summation happens, which is a linear regression, technically speaking. And this is the activation that I told you about. This activation part, remember, is a decision part. The weights, the weights are going to be updated by your strategy, the one that I was telling you about, the optimizer. And then this goes all over again. Now, when you are talking to computational scientists, they're going to call them hidden layers, because what is between the input and the output is hidden to the naked eye, because you can only see the input and the output. Most of the time, you cannot track what's happening here. So this is why the black box comparison comes from, because if you see here, what you have is something akin to a linear regression, but with matrices. So in your linear regression, you have, for example, the value you want to predict, and that could be just a vector. You have your intercept that relates to this bias part here, your slope, which is your weight, and your inputs where are here, but your inputs can be a tensor or a matrix of matrices. So in that sense, all can be related to a just linear regression, because you want to predict a value, and that value is already there. Your bias or your intercept is there also here. Now, it looks easy, but what it really sets things apart is the activation function. You see here how the weights are going up to this neuron part here that has the loss function inside, and it's trying to minimize the value closer to 0. And then the weights go up, and then they go back. The activation function here acts as a filter. If it goes to -1, it probably doesn't pass the information forward to the output. But if it goes to +1, it passes the output to the left part. Here we're using something called tangential hyperbolic tangent that goes -1 to +1. However, there are other activation functions that are more used. For example, the ReLU. It's a different kind. It just goes from 0 to positive values and then flat out here. But the important part here is that everything together is what goes over and over and over in the training. The part that goes back to here is the optimizer at work. And then the bias is important because the bias tells you how easy you will try to predict the next values. Meaning like trying to, this is a measure of your under or overfitting. Anyway, I hope this is kind of making it clear what happens inside of a neuron, because this kind of information visually is pretty much better to understand. The output is basically changing every time the weights are updated. All right. Now, like I was telling you, you have to control the randomness. This is why we set up the seed at the very beginning. Because in a neural network, each of these nodes will start from some number. It's just not zero. And you have to start those numbers at some point and better to be reproducible for the next point. Because in each training, every time that it goes back and forward, and you cannot reproduce and you cannot control that from the beginning, you will have a different answer every time you run this. So now, what I was telling you about the optimizer is that there is something called backpropagation. And we saw it in the code, really, really small, but you saw something like go back. And it was commented in the code, like this is the backpropagation. There are 3 lines only that define this process. The backpropagation is basically a forward pass, the flux of the information you want, and then you tell the program, okay, now update whatever these neurons contain back and go again in the training, but now you have different values here. And again, and again, and again. And this happens every time you do an epoch and every time you do a batch. Well, I already told you what's an epoch, but it does help to go like, okay, if you have training sets and you have sample, if you have to go through all of them, this is an epoch. Right. Now, in the loss functions, like I told you, we use one that is called cross entropy, categorical cross entropy. But you have also the binary cross entropy. And those are for different things. Binary because you probably have ones and zeros, and you can define your problem as 1 and zeros. Categorical, probably you have more than 1 zero. You have several. If you are predicting a value, probably you want to get this mean square error as lower as possible, because you're trying to literally predict from a range of 0 to 1, 0 to 10, or -1, or so on and so forth. But this is just to show you that you can alter this for everything, and this is why PyTorch is actually great. You can input whatever you want, even your own definition of a new loss function. And this is the stochastic gradient descent. I show you that this is the optimizer that we were using in that part of the slide. This is what it means. So for every time that you have an iteration, that loss function, you need to go all the way to 0. That's what it's doing here. And it's going to form a gradient. This gradient is a matrix, and we will see it in one of the notebooks that we have. One is called autograd. And this is all altered by a learning rate. So every time you have an iteration, it just compares the previous iteration to the next iteration and see if it has actually learned something, and updating all the information through the backpropagation in the neural network. All right? And of course, at the end of everything, remember that part that I was telling you, like this will actually tell you where are you in the steps of training and what's the value? Well, usually you should plot it like this. So you have here different scenarios. Like for example, this training was too long. And you see here, there is a curve of training and you have your loss function here. You want your loss function to go as closer as 0 as you can. And that's the training, that's what this curve is telling us. It's going closer to 0, to 0, to 0, to 0. That's incredible. The neural network is still learning, quote unquote. However, when you have your test set, that value doesn't go to 0 anymore. It just stays still. You gain almost nothing from going forward. So you should stop here in this epoch. You have to learn how to stop your neural networks, meaning that there is some thing called early stopping that you can input in your code. When you reach this point, when the validation is not going alongside the training, you should stop here. You will save time, your time, computer time, and probably money if you're using the cloud. Now, overfitting is the other part. It's like, oh, well, we're going closer to 0. This is not just improving, clearly overfitting. This is the other way around. It looks ideal. That's why I put it here. And as you see, the training goes down, 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 down. And the validation also goes down alongside it, but even lower. So here, it looks nice, but I would take a look at the data. If there is no data contamination there, if you're completely sure that the training data is completely independent of the validation data or the taste data, this is awesome. However, if it's not, or you're not 100% sure, this is just telling you that you're contaminating the training and you're relaxing the training too much. This will be underfitting. Okay, so that was all for the moment. Let's go back to the notebooks. Whoop. There you go. So we can skip this one because it's basic tensor manipulation. You can, just like many other things inside of Python and NumPy, you can basically add a tensor, subtract a tensor, multiplicate a tensor, division, modulo, power. Your regular arithmetic problems, you can do it with tensors. And PyTorch will allow you to do it. And you have several things here. And this is why I was explaining, like, at some point, somebody figured out that you could do these kind of operations inside of a GPU. So if you remember from your ancient history and mine, this was in algebra. You have a vector multiplying another vector, or it can be a vector multiplying a matrix. And then you have something very quick. As a response, this is computational time in a GPU, and it's very quick. So you can do the dot product of two vectors or two tensors, meaning the tensor could be very big, and it will do it very quick if you're in a GPU. The GPU is optimized for that. So in matrix multiplication, if you don't remember, you can actually multiply a matrix pretty quick just by summing up certain parts of it, and it will go very quick, and how it's shown here. And you can use torch matrix multiplication and the two tensors that you want to multiply. And this is pretty quick. As a matter of fact, try this one. Try this exercise. Go over the tensor, touch once, and then just multiply the same. You can cheat if you want. You can see the solution. I will give you a minute to go over it. But in the meantime, So use the same tensor and multiply by itself. Pretty straightforward, I guess. Of course, I didn't import Torch. By the way, here I put something that is very common to find, which is this part about the device. Actually, it auto-completes. That's nice. I don't want this. So Torch can actually tell you which one is the device if you do this. Like if you put if CUDA is available, it will try to determine if there is a GPU. If not, it will default to CPU. But CPU. Good. So torch.CUDA is available is going to be your best friend if you're using GPUs. It can default to something different. Usually this MPS is just for Macs, so I don't think you will find that very quickly or very often. But else CPU, like this, CUDA. Written like this is very often in the code. Search if there is a CUDA, meaning like a GPU over there. If not, use the CPU. That's fine. And then if I am correct over here, then yes, we can multiply the tensors. Okay, this one is nice, but I want you to go to the AutoGrad Python, AutoGrad notebook. This one is more related to what we just saw in the slides. So here is the AutoGrad part. When we are doing backpropagation, this is going to be our best friend. To compute, what you see here is basically a neural network, quote unquote, and let's say it's going to be it's a very simple diagram of a neural network that I found online. So in this case, you have your input as X, then you have your parameters and your bias, like I show you, and basically that's talking about the linear regression. Then you have your loss function, and you have your prediction here. So we want to update most of the time this part here, the bias and the weights. And this is why the backpropagation is important, right? When we are at this stage over here, meaning Z, C, and Y, we have to send back all the parameters. So Torch have something called AutoGrad, and that's going to be over here. Yes, run anyway. Oops. Let's kill this one. Many sessions, many sessions. Okay, let's see. Hit complain now, or do I have to manage sessions? Okay, let's kill these guys. You too. Close. Good. Perfect. Now I have torch. Okay, so to go a little bit closer to the speed of light, I'm going to cheat a little bit because I want to go down this road. So first we have our torch ones, we have our weights, we have our bias, and we have a way to go back. Of course, this is the expected output, and this is the loss function. Now we're going to use this cross entropy with logics, meaning that we have zeros and ones. So I put everything that you need to declare here. Like, for example, you need this requires grad because we're going to use autograd, meaning that we're going to send back the information to the weights and update them. Okay. Because when you put that you want them to have a gradient or grad, PyTorch takes notice of that, meaning that when you put this part here requires underscore grad, PyTorch would allocate a special place in the memory to say like, okay, so I have a map and now I have to get back to the point of the map when you told me, and to update those that have this property on. We want this one, the weights and the bias to be updated. This is why we need this flag to be true. Fine. You can see them here, but it's just the object that it creates inside of the memory. This is basically the map that it needs. And then we're going to compute some gradients. Now, when somebody tells you in this context what is a gradient, it means a matrix of changes. This is why it has here some deltas. There is the loss over the weight and the loss over the weight in both the input and the output. What does that mean? To optimize. This is there. Go back. Here. So, tensor gradients. When you're computing the gradient, what it means is like you're trying to create this matrix over here. Now, in the case of PyTorch, it's trying to create a matrix that is going to use something called Jacobian product. That's not too relevant in the sense that in the code you will not see it, but that's what it means. You're trying to create a bunch of different points that are changing over the time, and the program is taking notice of that, and it's just tracking the changes. That's a gradient, and that's what you are going to use to update the weights and bias. Okay, moreover, remember that I put something like no grad? So this no grad is exactly what that means. When you are not using this matrix anymore and you're just trying to predict, this torch.nograd will disable that part of going and update stuff and just plainly try to predict from your input to the output. Why was I putting here this? Okay. Been a year since I did this. Here and Perfect. The good part of having this all documented and in a place that it always runs is that it will run even if I don't update too much. That's great. Anyway, so in the autograd, in the tension gradient, this is the part that is important, just to update whatever you need to get back. So let's start from this example. For example, we're going to create this input here. So I is basically creating an identity matrix, meaning like it's a diagonal with ones and a bunch of zeros, and it will help you to do, just transpositions and other mathematical tricks. But then we're going to use this imp and create a tensor out by multiplying the matrix in by 3. Easy. Out equals then imp power. Yep, like this. My solution was like this. Yeah, it was different. So it's pretty much the same. I remember this one being different. Okay. So using the previous tensor out, let's create out backwards. Perfect. With the value matrix tensor 1. If we just run this, it goes to complain that I need a gradient that can be created, and I cannot do it if you don't tell me. This is the runtime error that is actually complaining. Hey, I need something to update. This is what it says. This is why in the solution we have in the backward you have this tensor that you will need to actually give to update that end. And then there is a part here that says retain graph equals true. This is the way PyTorch is keeping track of all the changes. Oops. Let's copy like this. Grad output has a shape of torch equal size and output 0. The shape has to be 4 and 1. So we can get this to the different shape. Torch. Okay. Why is out like this? Print out. Okay, I have my backward here. And this is why I need 4 by 5. We should be able to do this. Here. Live coding. Love it. We need something like this shape. Once. There you go. So what I got from here, it was like, it was complaining that this figure here, well, this shape over here was not matching what my input was supposed to be, because you wanted basically to update all this value here in this first call. If we do this a second time, there you go. So every time I do this, what I'm doing is updating this output here. This was my operation, right? I had an input. I basically did an operation there, which was like a power of 2. Perfect. This was the first result. And then it says, okay, I still have a memory of what these values were. Perfect. When I told him, now update with once that out and keep track of these changes, the first time it's actually updating it. And it's basically putting all the ones in the identity part. Well, where is not the identity, the ones. Okay, then the second time I do this, now it keeps updating the thing, and it keeps keeping track of that. And then this is the gradient, okay? So again, when somebody tells you a gradient in this setting, it means this. A bunch of changes, and because of this flag retain graph is true, it means that it goes and it's going to have not a version control, but a history of the changes that you're doing. And of course, input grad. Now let's return, yeah, and this is the thing. Once you have, for example, done this several times, and we did this just twice, but you can do it in a for loop for 1,000 times, and you go and change all the values. And remember, these are values for the weight and the bias. So at some point, you can say, hey, I don't want that anymore, and it's imp.0 .grad actually. So whenever we want to get back to the first part, like literally ending that updated cycle, we just go back and say like, okay, you have updated all the way here my input. It has created this gradient, but now I can go back and say like, hey, this gradient, put everything to 0. And it basically restarts everything, and you can go back and create another gradient and another gradient over and over and over again. So because you have this gradient and this, where is it? Here. This retain graph equals true. That means that this information goes to the memory. So at some point, you will run out of memory if you don't know how to manage this. But just take into account that you can do this. And in the code, you will always see something called backward that does exactly this. Okay? So the autograd is doing all these operations in behalf of you. You don't see it, but you can control it. And when you call backwards in the code, it goes back and it updates everything, reset things to 0, and start over. So this is hardcore deep learning stuff. But this is the details that you need to know. Okay. Now, data science. So there are 3 more things to go. I haven't tried this one actually in this setting, in the Google Colab. So this is the data loader part, okay? Now, check this one, try it, because it will try to download the MNIST dataset, but most likely it will fail because this was meant to be used in the binder setup. Now, check if you can download it to your Google Drive. Go ahead, read this notebook. As a matter of fact, go and copy all the solutions and check the error that it's going to give you, because probably it will tell you like, hey, I can download this, but give me access to Gmail, to Google Drive. Because if we do this, if you want to launch the binder, it should work over there. That's you. All right. So here in notebooks, I could go to data loaders here. Perfect. Now, the content of this notebook actually kind of reflects what you saw in the slide, but it's going to download something called Fashion MNIST. That Fashion MNIST, instead of having digits, it has clothes. But here it says load the CFAR dataset. Okay. Easy. Import torch, dataset, and transforms. Okay, we do this. Let's add one more piece, and then datasets. Good. Datasets dot CFAR. And we have the CFAR 10 here. Great. Now, if we go and say train, then I can do exactly what is held here. Root. There you go. Here's the parameter root. We're going to download here in a data folder. And then we're going to put train equals true, and then download equals true. Perfect. Now I do not have transforms yet here. And I could add transforms. And we're going to use this one, transforms to tensor. So let's declare transforms to tensor, and then transforms here equal transform. Perfect. That's one. Now for test, should be the same. CFAR, and then the only difference would be false here. True. That's fine. I just created that. Now, here it should be working because it has an asterisk, and it should be downloading right now to a folder called data. And I hope I don't run out of space in this binder. Okay. Train loader. Test loader are technically the same. Okay. Were you able to do it in the Google Colab? Were you able to download the CFAR 10 dataset? Or does it complain? This one is stuck here. Now, the reason that I put CFAR 10 is because it's one of the smallest datasets that you can actually get. The solution, pretty much the same. Yep. Ah, it failed for me. Okay, how about the collab? Were you able to do it? It fails. But does it actually ask you for permissions? Or just says, I cannot do it? Or something about the network. Sweet. Okay, let me catch up with you guys. Gosh. Four, two. Now, okay. Okay, this didn't work. However, allow. There is a workaround that I have in here. So it did fail for you, the download. I mean, for me, it hasn't changed anything yet. But you don't have a data folder, right? So one of the workarounds is mounting your own data, and is with these two lines here. Let's stop this one here for a second. Good. So from google.colab, import drive, and then drive mount /content/drive. So this one will connect to your Google Drive. You accept. It will take a little bit of time, but it will connect your Google Drive to this notebook in Colab. Okay, now it's mounted. Now we can use this variable parent dir, and we will input here to be the whole thing, content, my drive. Okay. Now, for the sake of being a little bit more clear, this one goes apart. Okay, and then code. Let's move this one out to test and code here. Sweet. So let's see if it works. In the meantime, this is a way of connecting Google Colabs with your drive. You have to basically mount it. And once it's mounted, in your Google Drive, you will find new files. I hope this is actually getting completed. We have a small terminal here. Aha. Oh. So for those of you that were here last time with the shell and git, you have a small terminal here that actually works like the bash that I told you last time. We have data here already because I put root as /content drive /my drive /data. Then inside of data, I still have nothing. Drive data, my drive data. Okay. It's taking its time. So it should be in drive /my drive /data, and there should be something there. I hope. Ah, it fails. Next time I will upload this beforehand. So bad. There is nothing we can do about it because it just fails. Sorry. Anyway, let's go to again. There we to open this here. Okay, sorry guys, this one is not possible to run because it needs to download the CFAR 10, which was supposed to be small, but not even in Colab allows it to download. Next time I will upload this into my own Colab, knowing this. Okay, moving on. What we can do then is practice exactly how you build the neural network. In the next one, in the 05 notebook, so you can practice exactly how you write the structure of the neural network, starting with torch NN. Okay. Now here's where it becomes really, really difficult to express the architecture that you want. And for this one, actually, I'm going to use the slide that I didn't want to get too much detail inside. Where is this guy? Here. Okay. So for that specific notebook, the 05, you're going to build something like this. A little bit different, but at the end, something like this. So now, getting more into detail, what is happening here? You see those numbers here, right? NN convolution 2D. In the notebook, you already have torch NN. So this is for neural network, and you're going to invoke all the small, all the backbone that you need. Now, check out. You have 1, 16, 3, and 1. What does that mean? Here, back in the input layer, it says it's a grayscale image. Imagine the Grumpy Cat, but just in grayscale. And it's an image of 28 by 28 by 1 channel, meaning 28 pixels by 28 pixels, and it's just gray channel. Perfect. Now, the first convolutional layer, what it's going to do, and I told you, it's going to reduce this 28 by 28 into something smaller. So it's going to use a kernel of 3, meaning that this is going to be 1, 2, 3, and 1, 2, 3, and it's going to go over the matrix that is this input grayscale. So it's going to generate then 16 different matrices with this sweeping. So this is the 16 that you see here. It's going to take 1 channel of input. It's going to output 16 channels, meaning like I have 1 matrix here, I will output 16 matrices. Now it's going to be reduced because I have a kernel of 3, and it's going to do a stride of 1. So it's going 1 column, the next column, the next column, the next column, then 1 row, the other row, the other row, the other row, 1 by 1. Because it's a convolution, those 16 matrices lose some of the information actually in the corners. And this is why these 16 matrices have 26 by 26. You lose some bits, you lose some pixels on this operation. That's fine. So the next step is to actually use the it's called the activation function ReLU. That ReLU, like you saw in the graph, is a decision boundary. So this decision boundary passes the information and then to another convolutional layer. And it does exactly the same. It will offset the 16 matrices that you output, and it's going to output double of that. You can ask the convolution to output less, but that's the thing. You have 16 and then you go 32 more, can be 64. But there are going to be now a bunch of different matrices. So basically 32 different matrices. This is a 32 here. And they're going to lose again some information because this is a convolution. It's 24 by 24, 32 times. Perfect. Yet again, you go and you check that activation function, and then the neural network decides if it passes or not this information to the next filter. Now, in this next filter over here is something called max pooling. Now, the max pooling is another way of reducing the information to the best you can. So an example of max pooling is over here. If you see each quadrant is a small matrix, think about that the kernel here passed through this over here, and it creates basically just 4, but it can create more, right? There is one in the center that it can create. But let's just put it on 4. So the kernel passes here, then passes here, then passes here, then passes here, because it has a stride of 2. And out of this quadrant here, it takes the maximum number, the maximum value. And then in the next quadrant, the maximum value. This is max pooling. Just getting the maximum value out of those small matrices that the kernel decides. And that's the max pooling that you see here. And because it reduces the name of inputs, this is why you have 12 by 12 by 34. The same 32 matrices, but now reduced in complexity, to speak. Now, in this backbone, you have something called dropouts. Those dropout layers are actually helping you to avoid overfitting or underfitting. Why? Because the dropout means that you're going to turn off certain amount of neurons randomly. So in the neural network, this dropout number here means like out of the number of neurons you have, you will randomly turn off 10%. So that means that 10% out of randomness, you will get rid of noise and valuable information. But just by statistics, it means that you will not be overfitting your information in the neural network. This is why you have a dropout here. Then these 32 things, these 32 matrices are going to put into just one big vector. So these 12 by 12 by 32 give 4,016 different slots, numbers, that basically this flattened function here, what it does is just concatenate each column on top of each other, on top of each other, and that's flattened. So the neural networks understand better this flattening thing, and this is why it's passed to a fully connected layer or a linear layer. So it does accept this flattening thing because you know already that you did a max pooling, and you know the input of that max pooling is going to come. So these fully connected neural network are all the neurons that I show you, and it's just in one block. So all these inputs pass to that neuron, and you get the information out of it. Okay, once you pass this fully connected layer, it does diminish the output. So you are telling it like you're going to get a huge input, resume that, and summarize it into only 64 different numbers. So here the mathematics, I don't know them. I'm pretty sure they're very complicated of what happens from this flattened to this part here, that it just reduces everything into 64 different bits. But again, this part here, use the ReLU function to decide if it passes or not what information or not. It's aided by a dropout again. So again, just randomly turning off different neurons, avoiding the overfitting. And at the end, the last layer will actually give you a variety of numbers that are the probabilities of one of the inputs was one of the numbers or not. So this AlexNet, this architecture of neural network is kind of convoluted in the sense that it has many parts. But if you look at like a puzzle, it's just connecting one after another. And it's connecting the output of one to the next one, just because you want to pass all the flux of information all the way to the last part when you use something called softmax, which is over here, that will give you a probability, and the highest probability of being associated to a number or not. This is the part that the label comes in. So the neural network has to learn a bunch of different things, because from one matrix you pass to have 16, 13 different matrices with different information. This is the learning part. There is numbers here that are ingrained in this architecture that ultimately will give you a probability, a high probability of being one or the other. But that's why the notebook number 6 is the one that you have to try to build a neural network. In theory, it should work, but as we saw, the data is not downloaded. I will fix that later, I promise, because I didn't know it wasn't going to download. But anyway, so far so good. Did I explain this in detail, like enough for you to understand it? Or do you have any question about this part specifically? All good? All right. So tell me, are you in the notebook of building the neural network? How far are you going? Is it possible to build the neural network in the Google Colab? Okay, let's go. Import. Perfect. It gives me the first part of the backbone. I import torch, I import NN, so I can build later, and then I import functional, which allows me to get the loss function. That's nice. Aha, too many sessions. I thought I canceled this. Okay. One more time. Good. Did I forget something? No. Nice. Get the device. So if we get the device equals, and then torch dot okay, over here, over there. This is more complicated than the one I got. Okay. This will check everything then. Using CPU. Okay, so here what I do basically is a very small linear, a very small neural network. Like I told you, the first part is importing, technically speaking, just the backbone. And this step forward is just the flux of information. So what I want is basically put a stack of things, and that stack of things is sequential, obviously. Now, in that sequence, I want to be a linear, just a flat, small thing with a small number of neurons, then apply ReLU, another linear, a little bit bigger, and then another ReLU, and then another linear. So basically speaking, what I'm doing is stacking neurons, neurons, loss function, neurons, loss function, neurons. That's the basic backbone. And it starts very easy. Then when I get the input, it will flatten that input, and then it will try to get those into a shape, passing that information through this, and it returns logits. Logits meaning zeros or ones. Okay, so you just have to copy this. And let's get here. Very easy. The thing here is like you want that neural network or that model to be into the device. So if you do neural network dot device to device, this will put your neural network into the memory. Torch.device. Okay. This one was missing. There you go. So now the model basically is living in the memory of the device. Fine. Create and move the model. Okay. That was it. So I have this here. This should be down there. Now, to use the model, we pass input data. This executes models forward alongside the operations, like you define it over here. Whenever you have, what's this? Okay. Whenever you have an input, the model doesn't use this. It uses this one. Use the definition of forward. It takes the input, flattens, and then it passes to this part here, the backbone, one after another. We don't have model forward directly, but there is no data here. Okay. Now, for this one, we can create a random, where are you? Here. So in the exercise 4, then we can create a random tensor input, get the logits, and apply softmax to determine each class. That's pretty much what we want to do. So were you able to reach this point? Yes, perfect. So the one that fails is the data loaders. That's something I will fix later. All right, were you able to go all the way down? Perfect. So if you were all the way down to model parameters and then printing the structure of the model and parameters, I'm glad that this actually works, and it's very simple to have. Now, if you completed this, you have already a very strong idea of how to build a model. That's how you build models in PyTorch. You use the class, you use the forward, and then you start going over the training loop. So now, last but not least, Finder is down. Let's go down here, leave here. Nice. Now, data science. Now, the last one, if I'm correct, it will not work because we'll require to download the data. Yes. Okay, so we can stop here because this one will not work given that we could not download the CFAR. And this one will not be able to download the CFAR. But I will work in the afternoon to update this. So you can use it with Google Colab instead of failing here live. Okay, so for the moment, this is just what you need to know how to train the model. The data loaders failed, but the data loaders basically allow you to just pick up stuff from different databases that already have. The most important part, if you could build the model, then you can throw any architecture that you want. So Notebook 5, if you want to rebuild the model, go ahead, play with it. Check that you can basically do whatever you want with it, as long as you put the backbone first and then the flux of information down. Just like we did with AlexNet. Just to not let you go without, or you're empty-handed. So the last part, and I didn't put that here, but there is another repo that you can check. So if you're interested in not only doing your normal training, you can use this repository. This was another workshop that I did last year about how to find the best parameters for your PyTorch model. This one also have your regular notebooks here, and you have also, not this one, a notebook that has a link to Colab. Now, for these ones, you will need to connect to the GPUs that are freely provided by Google. In this case, I am connected to this small GPU hosted in T4. That's a Titan GPU. So in these notebooks, what you will find is a bunch of different information about hyperparameter optimization with different libraries, and especially how to use another library called Rapids. I am an NVIDIA DLI trainer, an ambassador for the university. If you saw last December, I gave a workshop about Rapids, and you can get a certification for that when you come to that workshop, and it's not recorded, by the way. It is live only, but the gist of that is like you can use GPUs now, and with these examples here, you can go over different stages of how to prepare the dataset, how to run it in the memory of a GPU, and how to, at the end, get the best hyperparameters, meaning the number of layers, number of neurons, optimal learning rate, probably even the best search strategy, not only SGD. You can try to get different strategies tested and benchmark and get the best out of the code and flexibility of PyTorch. Now, this one, for example, use another library that's called Optuna, pretty famous, pretty good, because it also allows you to visualize the results. But, well, this is a tale for another time. But please, if you have any other questions, go ahead, search for this one. Go back. This repository, Rapids HPO, you will see my face over there because it's in my repository, in the notebooks, and then you just open your Colab and you can run it. It's a different topic, but at the end is what is next after this one. If you already know PyTorch, you can use this one just to accelerate PyTorch. Okay? So, any more questions? Good. I promise I will fix that thing with the CFAR for the data loaders and for the last notebook, because apparently we're running out of space in this institution, which is odd. But anyway, so if you're okay, you can now have more coffee and more cookies. Take it. You already passed through a lot of different things, a lot of different concepts. I hope it was clear. If you don't have any other concept clear, please come. We will chat and we will get through it for sure. Anyway, so thank you for coming. I hope it was useful or at least not confusing. And I give you your time back. Thank you so much for coming. Okay. Close.